Hello everyone. Here we shall solve some more KCET previous year questions on the chapter thermal properties of matter. And in the previous part of this chapter, we had solved from question number 1 to question number 15. So in this part 2 of this chapter, we shall solve from the question number 16 onwards. Uh, so if you have any questions or doubts in the solutions, then please write us in the comments section. And if you feel that you have more difficulty in any of the chapters of physics, then also please mention the name of that chapter in the comment section, so we shall give more priority on it and solve more and more questions on that chapter. Also, the homeworks on every chapter will be uploaded in the Sapience Education application. So please install our Sapience Education application, whose link has been provided in the description. So we shall start off with the question number 16. So here it is told that a hot body is allowed to cool down. The surrounding temperature is constant at 30 degree Celsius. The body takes time t1 to cool down from 90 degrees Celsius to 89 degrees Celsius, and time t2 to cool down from 60 degrees Celsius to 59.5 degrees Celsius. So from 90 degrees Celsius it cools down to 89 degrees Celsius in time t1 seconds, in time t1, and it cools down from 60 degrees Celsius to 59 degrees Celsius, 59.5 degrees Celsius in time t2. So now therefore we have to find the relation in between t1 and t2, and the surrounding temperature theta is, that is equal to 30 degrees Celsius. So now here we have to use the law, the Newton's law of cooling. So therefore according to the Newton's law of cooling, we can say that theta 2 minus theta 1 by t, that is equal to k into theta 1 plus theta 2 by t minus, theta 1 minus theta 2 by plus theta 1 theta 2 by 2 minus theta s so that will be okay. So I think we have told in one previous question also. Yeah, so this was the concept. Okay, so here also the same concept we have to apply. So here in the first case, so theta s is 30 degrees Celsius and theta 2 is 90 degrees Celsius in the first case, and theta 1 is 89 degrees Celsius. So therefore we can say that 90 degree minus 89 by t1, that is equal to k into 90 plus 89 by 2 minus 30. So that will be 1 by t1, that is equal to k into so this is 89.5 minus 30. So therefore 1 by t1, that is equal to k into 59.5. And then in the second case it is 60 minus 59.5 divided by t2, that is equal to k into 60 plus 59.5 divided by 2 minus 30. So therefore we can say that this is 0.5 by t2, that is equal to k into, this is 59.5 plus 0.5 by 2, that is 0.25. So this is 59.75 minus 30. So therefore I can say 1 by 2 t2, that is equal to k into 29.75. So therefore 1 by t2, that is equal to k into 2 into 29.75, so that is so 1 by T2, that is equal to K into, so 2 5s are 10, 2 7 are 14, that is 5, and 2 9s are 18, 9, 2 to the 4, 59.5, so K into 59.5. So therefore we can see that K into 59.5, that is also equal to 1 by T1, that is also equal to 1 by T2. So it means that T1 is equal to T2. So the same time is required. So T2 equal to T1. So option D is the correct answer. Then here it is told that a solid cylinder of radius r made of a solid cylinder is there of a solid cylinder of radius r made of a material of thermal conductivity K1 is surrounded by a cylindrical shell of inner radius r and outer radius 2r. Outer radius is 2r and inner radius is r, made of a material of thermal conductivity K2. The two ends of the combined system are maintained at two different temperatures. The two ends of the combined system are maintained at two different temperatures. Then there is no loss of heat across the cylindrical surface and the system is in steady state. The effective thermal conductivity of the system is. So now, so here yes. Okay, so here the two ends of the combined system are maintained at two different temperatures. Then there is no loss of heat across the cylindrical surface. The system is in steady state. So here it means that so here is a cylinder and outside there is a cylinder. So the effective thermal conductivity, so here so we know that dq by dt, that is equal to ka dt ka delta theta by delta x, where dq by dt is the rate of flow of heat by thermal conduction. Now that is delta theta, which is the change, which is the temperature difference, and this by delta x by k. Now delta x by k is called as the thermal resistance. Now since these two conductors are connected in parallel, they are connected in parallel, so uh, uh, they are acting as parallel resistors. So when they are acting like parallel resistors, then 1 by R equivalent, it means that if it is replaced by one single equivalent resistor, one single equivalent conductor which is having the thermal resistance as R equivalent, then we can say it is 1 by R1 plus 1 by R2, since they are connected in parallel. So now here R1 that is equal to length is same, radius, okay, so L by this is K1, L by K1 into A, area will be area of the outer cylinder, that will be equal to pi, area of the inner cylinder, that is pi r square, and r2 will be equal to L by, now length I am taking this length of the two cylinders, L by this is K2 into pi into 2r whole square minus r square. So this is 4r square minus r square, that is 3 pi r square. So this is L by K2 into 3 pi r square. Therefore, the effective thermal conductivity of the system. Okay. Now therefore, R equivalent means R equivalent I can write that is equal to L by K effective or K equivalent or K effective which is the effective thermal conductivity into A. Area of cross section will be 4 pi r square. That's pi into 2r whole square. Okay, so therefore we can say L by K effective 4 pi r square, that is equal to L by K1 into pi r square plus L by K2 into, sorry, this is inverse of this. Okay. Inverse of this means 1 by this L by K2 into, since why this we can write it as R equivalent inverse, that is equal to R1 inverse plus R2 inverse. Okay. So therefore you can say this is K2 into 3 pi r square whole inverse. Okay. So now this can be written as 4 pi r square into K effective divided by L, that is equal to K1 into pi r square divided by L plus K2 into 3 pi r square divided by L. So L and L that will cancel, pi r square that will cancel. So this will be 4 into K effective, that is equal to K1 plus 3K2. So therefore K effective will be equal to K1 plus 3K2 divided by 4. K1 plus 3K2 divided by 4. So option D is the correct answer. Okay, then two stars A and B radiate maximum energy at the wavelengths of 360 nanometer and 480 nanometer respectively. Then the ratio of the surface temperatures is, so lambda m into T, that is equal to B. It is called as the Wien's displacement law. So here we have to use the Wien's displacement law. Here lambda m is the wavelength corresponding to the maximum intensity of radiation, and T is the surface temperature, and B is the Wien's constant. So now therefore we can say that lambda m, that is inversely proportional to T, since B is a constant. So therefore lambda m1 into T1, that is equal to lambda m2 into T2. So therefore the ratio, the two stars radiate maximum energy at these wavelengths. So therefore lambda ma divided by lambda mb, that is equal to Tb divided by Ta, which is the ratio of, now the ratio of the surface temperatures of A and B has been asked. So it means that Ta by Tb has been asked. Ta is to Tb, that is asked. The surface temperature of the star A is to the surface temperature of star B, that has been asked. So this will be Ta by Tb will be lambda mb by lambda ma. So the wavelength where the maximum intensity of radiation from star B, that is 480 nanometer, divided by the wavelength of maximum intensity of radiation for star A, that is 360 nanometer. So if we have to cancel out these two, so 0 0 will cancel, 12 3 are 36, 12 4 are 48. So that is 4 is to 3. Since it is coming 4 by 3, so 4 is to 3 is the answer. Option C is the correct answer. Then here it is told, in anomalous expansion of water, at what temperature the density of water is maximum. So we know that the density of temperature is maximum at 4 degrees Celsius. The density of water is maximum at 4 degrees Celsius. Since why? If the water is converted to the ice at 4 degrees Celsius, then its density decreases. So at 4 degrees Celsius the density is highest, and if we heat it then also the density decreases. The density of water is maximum at 4 degrees Celsius, which is 1 gram per centimeter cube. So option B is the correct answer. Then 1 gram of ice is mixed with 1 gram of steam. So 1 gram of ice which is kept at 0 degrees Celsius, it is mixed with 1 gram of steam which is at 100 degrees Celsius. So then the temperature of the mixture is, so it means that both will convert to liquid water, both will convert to the liquid water. So it means that 2 gram of liquid water will be obtained, 2 gram of liquid water at temperature theta degree Celsius, suppose say. So that theta we have to find. What is the temperature at thermal equilibrium? So when ice will convert to water, then there will be some latent heat. There will be some absorption of latent heat, and when steam will convert to water, then also there will be uh, a release of the latent heat. Means that the latent heat will decrease. So it will, ice will first convert to water at 1 gram of water at 0 degree, then it will convert to uh, liquid water at theta degree Celsius. So therefore, according to the principle of calorimetry, we can say that calorimetry, the heat lost by the hot body, heat lost by the hot bodies, heat lost by the hot body, that is equal to the heat gained by the cold body, heat gained by the cold body. So now therefore heat lost by the hot body. So first 1 gram of ice will lose the latent heat, which is m into L, which is the mass m is 1 gram, m into latent heat of ice into latent heat of into the latent heat of fusion, actually latent heat of fusion, plus that will be mass into uh, water, specific heat of water into heat lost, sorry, that is okay, heat gained, that will be actually theta minus 0 is equal to, that will be heat lost by the steam. So first it will lose the latent heat of vaporization, that is m into latent heat of vaporization, plus it will lose the heat, it is m specific heat of water into, it will lose, then there will be the decrease in the temp. First the steam at 100 degrees Celsius will convert to water at 100 degrees Celsius, then that water will convert from 100 degrees to theta degree Celsius, where theta is obviously greater than 0 and less than 100. So it will be 100 minus theta. So all these masses will cancel out. So now the latent heat of fusion of ice, that is how much? So the latent heat of fusion of ice is 80 calorie per gram. So now we know that latent heat of fusion of ice, that is equal to 80 calorie per gram, and latent heat of vaporization of water, latent heat of vaporization of water that is okay, latent heat of vaporization of water 540 calorie per gram. Okay. So the latent heat of vaporization of water is 540 calorie per gram, and the specific heat capacity of water, that is the specific heat capacity of water, that is 1 calorie per gram per degree Celsius. Specific heat capacity of water. Okay. So therefore we will place the values and find the answer. So therefore L here we got, that is L fusion, the latent heat of fusion plus specific heat capacity of water into theta, that is equal to the latent heat of vaporization of water plus the specific heat capacity of water into 100 minus theta. So therefore we can say this will be latent heat of fusion, that is 80 plus 1 into theta, that is equal to latent heat of vaporization, that is 540 plus specific heat capacity of water, that is 1 into 100 minus theta. So this we will solve. So this will be 80 plus theta, that is equal to 540 plus 100 minus theta. So this will be 2 theta. 2 theta will be equal to 540 plus 100 minus 80. So 2 theta will be equal to 540 plus 20. So therefore 2 theta, that is equal to 560. So therefore theta will be equal to 200. Okay, so that is theta, that is equal to something wrong here. Okay. So now the ice will actually convert to the steam. So wait, there is something wrong here. So here the first thing is, sorry. So here actually first we have the steam. We have the steam which is 1 gram. So it contains a latent heat which is 540 calorie. the latent heat of vaporization it is having. Now ice which is having 1 gram, it needs 80 calorie to convert to the 1 gram of ice we have, which is at 0 degree Celsius. So it requires 80 calorie to convert to 0 degree Celsius water. So therefore, if it takes away from the steam, for converting to steam at 100 degree Celsius, so it requires 100 ms delta T. M is 1 gram into S, which is 1 calorie per gram, into 100 degree Celsius per gram degree Celsius. So 100 calorie it needs to convert to 100 degree Celsius water, and then this 100 degree Celsius water needs again 540 calorie to convert to the steam. So so it means that to 1 gram of ice, if I give 180 calories, then it will convert to 1 gram of water at 100 degrees Celsius. Which it can take from here only, which it can take from the steam. So it means that the full steam 1 gram. So out of this, only some part will be converted to 100 degrees Celsius water. So the temperature of the mixture will be 100 degrees Celsius only. So option A is the correct answer. Then in question number 21, water is heated from 0 degrees Celsius to 10 degrees Celsius. Then its volume. So from 0 degrees Celsius to 4 degrees Celsius, the density decreases, and from 4 degrees Celsius to 10 degrees Celsius, from 0 degrees Celsius to 4 degrees Celsius, the density increases, since the volume decreases. Okay, density of ice is less than density of water at 4 degrees Celsius. So then after 4 degrees Celsius, again the density decreases. So the density of water is highest at 4 degrees Celsius. So from 0 degrees to 4 degrees Celsius it increases and then again decreases. So first so the density increases, so therefore the volume first decreases and then increases. So if I plot the volume with temperature, then from 0 to 4 degrees Celsius the volume decreases and then the volume increases. So option B is the correct answer. It means the volume first decreases and then increases. Then here it is told, a pan filled with hot food cooks from 94 degrees Celsius to 86 degrees Celsius in time equal to 2 minutes. When the room temperature is 20 degrees Celsius, so it means temperature of the surrounding theta is 20 degrees Celsius. And how long will it take to cool down from 74 degrees Celsius to 66 degrees Celsius? So that time interval is being asked. So now according to the Newton's law of cooling, we can say that theta 2 minus theta 1 by t, that is equal to k into theta 1 plus theta 2 by 2 minus theta s. So now theta 2, that is theta 2. So in the first case I will use, that is theta 2 is 94, so 94 minus 86, it will cool down from 94 to 86 in a time interval of 2 minutes. 2 minutes, and here this is degree Celsius obviously, and this is k into theta 1 plus, so 86 plus 94 divided by 2 minus 20, so this will be 8 by 2 degrees Celsius per minute. That will be equal to k into, this will be 90, so 4, this is 90, 90, this is 90 minus 20, so k will be equal to 4 by, now this is degree Celsius, so this will be 4 by 70 per degree, so sorry, per minute, per minute, it will be minute inverse, it's coming in minute inverse. So this is the constant k which is used in the Newton's law of cooling. Okay, so now this constant we can use in the second case. So in the second case, it cools down from 74 degrees Celsius to 66 degrees Celsius, so therefore I will write 74 minus 66 by t, this time interval we have to find, we are being asked to find that t by t, that is equal to k into 74 plus 66 by 2 minus 20, since the surrounding temperature is 20. So this will be 74 minus 66, that is 8 obviously, 8 by t, that is equal to k is 4 by 70 into, that is so 60, this is 4, 70, 140 by 2, that is 70 minus 20, so there is 50. So 8 by t, that is equal to 4 by 70 into 50. So 0 0 will cancel, 4 2s are 8. So 2 by t, that is equal to 5 by 7. So therefore t is equal to 14 by 5. 14 by 5 minutes it will take, minutes. So therefore that is 2.8 minutes. 2.8 minutes it will take. So option B is the correct answer. Then here it is told 4 rods with different radii and length L are used to connect 2 heat reservoirs at different temperatures. Which one will conduct most heat? Which one will conduct most heat? Okay. It means the rate of flow of heat should be the fastest. Different radii, length L. So 4 rods are used to connect. Two heat reservoirs at different temperatures. Okay. So here is a heat reservoir, here is a heat reservoirs. They are connected at 2 different temperatures, theta 1 and theta 2. So let's say theta 1 is greater than theta 2. So heat is flowing from here to, from point A to point B. So this is also of length L, this is also of length L, length L, length L, and all are having radius R. So therefore you have to find dq by dt, that is equal to k effective into A is pi r square into theta 1 minus theta 2 divided by delta x, which is 4L. Now therefore k effective, that will be equal to okay, so it means that here they are connected in series, so R equivalent, that will be equal to R1 plus R2 plus R3 plus R4. Now here all thermal resistances will be same, since all are having length L and area of cross section also are same. So that will be 4 into R, it will be 4 into L by Ka, which is pi R square. So 4L by K effective into pi r square, that is equal to 4L by k into pi r square. K into pi r square. So k effective is equal to k only. So k effective is equal to k, which is equal to k effective is equal to k only. So therefore, the rate of flow of heat by conduction, that is proportional to r square by L. So if r square by L value is higher, then the rate of flow of heat would be higher. So now here for the first option, r square by L, that is equal to 1 centimeter whole square by 1 meter. So that is 10 power minus 2 whole square by 1. So that is, in meter it will come. So that will be 10 power minus 4 meter. And for the second option, r square by L value, that will be 1 centimeter whole square divided by half meter. So that is 10 power minus 4 divided by half. So that is 2 into 10 power minus 4 meter. And then option C, that is r square by L value, that is equal to 2 centimeter whole square divided by 2 meter. So that will be 2 into 10 power minus 2 whole square by 2 meter. So that is 4. So 2 into 10 power minus 4 meter. So option B and C are having same value of r square by L. And option D, that is r square by L value, that is 2 centimeter whole square divided by half meter. So that will be 2 into 10 power minus 2 whole square meter divided by, this is half meter. So this will be 4 to the 8 into 10 power minus 4 meters. So this value is the highest. So the r square by L value is highest in the option D. So it will conduct most heat. So option D is the correct answer. It will conduct the most heat. So in question number 24, it is told that a cup of tea cools down from 65.5 degrees Celsius to 62.5 degrees Celsius in time interval of 1 minute in a room of 22.5 degrees Celsius. So the surrounding temperature here is 22.5 degrees Celsius. And how long will it take to cool down from 46.5 degrees Celsius to 40.5 degrees Celsius in the same room? So same room means the surrounding temperature would be the same, which is 22.5 degrees Celsius. So here the time required will be how much, that we have to find. So now therefore, according to the Newton's law of cooling, we can say that theta 1 minus theta 2 divided by t, that is equal to k into theta 1 plus theta 2 by 2 minus theta s. So in the first case, we have theta 1 is so 65.5 minus 62.5 divided by t1, that is 1 minute, and this is in degrees Celsius, that is equal to k, which is the constant in Newton's law of cooling, into 62.5 plus 65.5 divided by 2 minus theta s, which is 22.5. So this will be 3 degrees Celsius per minute, and that is equal to k into, this will be 62, so this is 127, so 128 by 2, that is 64 minus 22.5, so 64 minus 23, that is 141, so that is 41.5, k into 41.5. So therefore the value of k will be 3 by, and this is in degree Celsius, so this is 3 by 41.5 per minute, 3 by 41.5 per minute. Therefore in the second case, you have to find the time t. So 46.5 to 40.5, this t we have to find, right? So therefore that will be 46.5 minus 40.5 divided by t, that will be equal to k into 46.5 plus 40.5 divided by 2 minus theta s, that is 22.5. So this will be equal to 6 by t, that is equal to k into, this is 126, so this is 86, so 87 by 2, that is, it is 2 4s are 8, 2 3s are 6, 43.5. Minus 22.5, so that will be 6 by t, that is k, which is 3 by 41.5 into, this will be 21, it's 21, so therefore 3 2s are 6, so k will be, so sorry, t will be equal to, it's 21t, that is equal to 2 into 41.5, so t will be equal to 41.5 into 2 divided by 21, so this is 2 5s are 10, 2 2s of 1s are 2, 3, 4s are 8, 83 by 21, 83 by 21 minutes it will take, so which is approximately 84, so it is approximately 4 minutes, 4 minutes approximately 4 minutes, slightly less than 4 minutes it will take. So option A is the correct answer. Then here we shall solve the last question of this chapter. Okay, so is a sphere, a cube, a thin circular plate, all of same material. So a sphere is there and one cube is there, and one thin circular plate is there, thin circular plate is there, all of same material, they are having same material and same mass, they are having same mass also, and they are having same material also, same material. It means they are, okay, initially heated to same high temperature, so their theta initial, that is theta naught, that is same, same material, it means their thermal conductivity is also same. They are allowed to cool down under similar conditions, then the plate will cool down the fastest and sphere the slowest. So here what will happen, so they are having same mass and same material, means they are having same density also, density is also same. So for the thin circular plate, the exposed area is maximum, since it is very thin, so therefore the thickness is smallest, so thickness is the least for the circular plate, so its surface area is maximum, so So its surface area is maximum. So when the area is maximum, then the rate of thermal radiation will be highest. When the surface area is highest, when the surface area increases, then the rate of heat radiation also increases. Rate of heat radiation also increases. So it means that the plate will cool down the fastest. The plate will cool the fastest. Okay, the plate will cool the fastest, and which one is having the least surface area, that will cool down the slowest. So the density of the sphere and the density of the cube is the same, and their mass is also same, so their volume also should be the same. So if a sphere and a cube are having the same volume, then which one is having having lesser surface area, that we have to find. So now the volume of the cube, suppose here each side length is x, then the volume of the cube is x cube, and here if the radius of the sphere is r, then the volume is 4 by 3 pi r cube. So now therefore 4 by 3 pi r cube, that is same as x cube. So therefore x is same as cube root of 4 by 3 pi, cube root of 4 by 3 pi into r. So now the surface area of the sphere, that is equal to 4 pi r square, and the surface area of the cube, that will be equal to 6x square, 6 faces and each side is a square. So 6 into 4 by 3 pi whole power 2 by 3 into r square. So now if we take the ratio, now therefore 4 pi, that is equal to approximately, that is 4 into 3.14, that is approximately 14 4s are 56, 4 6 are 12.56 approximately, and the value of 6 into 4 by 3 pi whole power 2 by 3, so this is approximately 6 into, so 4 by 3 so this is 4 divided by 3 into pi equal to whole power 4 divided by 3 into pi whole power 2 divided by 3. So that is approximately 2.6 approx. So this will be approximately, so into 6, so that is approximately 15.6 approx. Approximately that is 15.6. So approximately this is 15.6 and this is 12.56. So therefore obviously the surface area of the sphere is less than the surface area of the cube, if both have the same volume, therefore when the exposed surface area decreases, then the rate of flow of heat due to thermal radiation, or then the rate of heat radiation will be lesser, will be slower, I can say. The rate of heat radiation will be lesser. So therefore the sphere will cool down the slowest. The sphere will cool down the slowest. So the sphere cools down the slowest since it has the least surface area among all the three. And and the since the surface area of the plate is the highest, so the plate will cool down the fastest. So the plate the fastest and sphere the slowest. So option A is the correct answer. So here we shall end our class on this chapter. So hope you have understood all the solutions of these questions. If you have any more uh, doubts in any of the questions, or if you are not able to understand in any of the steps of the solutions, then please write it in the comments section, and please install our Sapience education application, since the homeworks on these KCET problems will be uploaded, uh, which would be helpful for your KCET exam. So thank you everyone.